Video lesson number 12, reaction rate and chemical equilibrium. Well, reaction rate is simply how fast a chemical reaction proceeds. Much like we can measure how fast a car goes, for example, in miles per hour, we can measure how fast a reaction proceeds. Now, we don't measure in miles per hour or a change in distance over time, but what we do measure is the change in concentration over time. So if we had a generic reaction, reactants turn into products, correct? So over time, our reactant concentration or amount is going to go down, and our product concentration amount is going to go up over time. So we could measure it either way, depending on what's easier in the lab. So we can measure in a change in the concentration of the reactants over time, or a change in the concentration of the products. Now, we then got into collision theory and the conditions necessary for a chemical reaction to occur. So I said that's much like hitting a home run in baseball. Three things have to happen. You have to have a collision, we have to have a contact between the reactants. Number two, there needs to be enough energy. And number three, we need the correct orientation of the reactants in order for the reaction to happen. So much like a batter who swings at a pitch, not every time he swings at a pitch he's going to hit a home run. What has to happen? Well, he's got to hit the ball. A. B, he's got to be swinging hard enough for it to go over the fence. And C, he has to hit it in just the right spot. Hits it on the top, it's going to go on the ground. Hits it on the side, it's going to be a foul ball, etc. So we got the idea of the conditions necessary for a reaction. Now, this animation kind of shows you that as hydrogen and chlorine are going to react here, they do have a collision, but notice not enough energy. So that's just kind of like a weak swing at baseball. We're not going to have enough energy for that reaction to occur. No home run. Here we have a lot of energy, so we take a hard swing, but we didn't have good orientation. So we had an indirect collision. Again, no reaction. All three conditions have to be met. We have to have hit hard enough in just the right spot, and then we get a chemical reaction. Okay? Now, with that understood, we can now talk about factors that affect reaction rate. Again, all of them, if you increase, for example, concentration, will affect the reaction rate. How is that going to happen? Well, more particles would mean more collisions, means more reactions over time. Thus, we have an increased rate. Increasing the temperature will also result in more collisions over time because the particles are moving around faster. And if we thought about our second factor, it also gives us more energy. So each collision is hitting harder, so we're more likely to have enough energy for the reaction to happen. Okay? Number three, the surface area. That is really just a measure of the area where we can have contact. The smaller the pieces of our reactants, or the more broken up it is, the more places there are for collisions, the more reactions then can take place, and so that will also increase our rate. Okay, and lastly, pressure affects only gases, because remember that the particles in a gas are far apart. Molecules in a liquid and a solid, for example, which I have a little model here, are close together. So if the particles are far apart, they can be pressed together or pushed together with applied pressure. That makes a reaction more likely to happen because there's more likely to be a collision. Lastly, we talked briefly about catalysts and how they speed up chemical reactions, and they do so by lowering this thing called the activation energy, which you can see on this graph. Now, you might recall or just keep in mind from our last unit that this is an exothermic reaction because the products have less energy than the reactants, so we're losing energy in this reaction. This is the normal pathway as we proceed. Now, even in an exothermic reaction, notice that it doesn't just happen automatically per se. We have to overcome this speed bump, I called it, which is really the activation energy, or the EA, in order for the reaction to occur. So my reactants must have enough energy to get over this before they can become products. The way a catalyst works is by lowering this speed bump. So the pathway with the catalyst, you see that the activation energy has been lowered. And I'll show you that animation again in a little bit that will help drive that point home. Okay. From there, we went on to talk about chemical equilibrium. And to understand that, we had to realize that most reactions are actually reversible. So in this case, we have nitrogen and hydrogen forming NH3 or ammonia. That's a combination reaction. But this reaction not only proceeds in this regular forward direction as reactants make products, but we said that at the same time, the products are breaking down to form reactants. And so it would really look something like this, where they're both, again, happening at the same time. Eventually, reversible reactions will reach a state of equilibrium, which we defined as a state of balance. It's dynamic in the sense that the forward and reaction are occurring at the same time, but it's a state of balance, okay? And we gave the illustration of the escalator and the shopping mall, which I have this example on the board. We said initially, right, we have a lot of people on the first floor. They move up to the second floor, right? But as we get more and more people on the second floor, people start coming down to the first floor. So it's a dynamic thing as people move up and down. But when we hit this point where the amount of people going up is equal to the amount of people going down, we could all agree that the number of people on each floor now is not changing. And that's equilibrium. So the two conditions where the rate of the forward and reverse reaction are equal, and at that point the concentrations will be constant. Okay, we then use the PhET simulation from the University of Colorado at Boulder. These are very useful simulations to show the reversible reaction. And I wanted to show you a couple things here. The first thing is as we start, normally we started with a lot of A, right? A turning to B is the forward reaction, B going to A is the reverse reaction. So just to start us off here, notice if I bring this up, this is my activation energy. The rate of A going to B is super, super slow. So if we thought about how a catalyst works, this is a great way to visualize it. A catalyst works by lowering this speed bump, and now the reaction, you can see A to B is happening much quicker. So that was the idea of a catalyst. Now, so we're going to let this sit here for a little bit. We'll show the species information. And notice we're going to hit this point. You can see the A's are turning into B's, but B's are also turning into A's. We hit this point roughly around now where we've hit equilibrium. So we've got basically the rates being equal as the amount of A's turning into B's is equal to the amount of B's turning to A's as the balls bounce back and forth. So you can see our concentrations here are relatively constant. Okay. So we then talked about Le Chatelier's principle, which predicts what will happen when you stress an equilibrium system. So this is a good way of seeing that. If we just look at the numbers, for example, what if I added a bunch of A to the system? Okay, so if I increase the number of A, so we'll crank it way up there, notice how the system reacts. The system reacts by shifting the equilibrium to the right and making more B. So you can see my B number going up over time, and now we're going to reestablish a new equilibrium. Okay. Likewise, if I removed A, so we probably hit that equilibrium right about now. If I decrease A, notice what will happen. So if I take away A, the equilibrium now is going to act to shift to replace what I took away. So now it shifts to the left, and we start to make more A. So that's the reverse reaction happening there, and I reestablish a new equilibrium. So that was Le Chatelier's principle in action. And again, just to review the principle, if you stress a system at equilibrium, the system shifts to relieve the stress. If you add a reactant or product, it's going to shift to remove the reactant or product. If you remove a reactant or product, it's going to shift to replace what you took away. So we got into a few examples, and I want you to be able to think through these. So here's a good example. And again, notice we're going to talk about our stresses. So we're going to add heat, we're going to remove N2O5, and then we're going to add pressure. So first up, if we're talking heat, we should at least recognize that this is an endothermic reaction because heat's a reactant. So if I add heat to this, the system is going to shift to relieve the stress. Okay? So in this case, since heat is a reactant, making products relieves the stress, and so the system will shift to the forward reaction, or favor the forward reaction, and we're going to get the following results. So N2O5 is going to go down, and the amount of NO2 and O2 would then increase. Okay? If we removed N2O5, so again, think back to the simulation we just looked at. A and B, so I removed A, the system shifted to replace what I removed. So if I take N2O5 away, the reverse reaction favors the production of that. So the equilibrium here will shift to the left, as now my products make more reactants to replace that removal. And so my concentrations of both of my products, NO2 and O2, will go down. Okay, the tricky one was pressure. So remember, pressure only affects equilibrium systems involving gases when there's an unequal amount of gas on either side. So remember, we measure that amount in moles by these molar coefficients. So we have to look at the equation. Number one, we see that there's G's here, so we got gases. Here on the left are the reactants, we got 2 moles of gas. Here on the right, we got 4 plus 1 is 5 moles of gas, so clearly unequal. So if I add pressure, the system is going to shift to relieve the pressure. Okay? So I got to ask myself, which way relieves pressure? Less moles or more moles? Well, less moles, okay? Because less moles means less particles. Less particles means less collision, less pressure. So which way gives me less moles? Is it towards 5 or is it towards 2? Well, clearly that's towards 2. So my reaction in this case would shift to the reverse reaction. So there it is. There's my reverse. And so what would happen over time to N2O5? Of course, that would go up because I'm making more of that, and NO2 and O2 would both go down. So I hope that was helpful. I'll see you in class.